Welcome everyone. Now we're going to discuss spherical coordinates. So this is another way you can set up a triple integrals if you have a specific solid in space. So it's very similar to cylindrical coordinates, but a little bit different because we're going to redefine our x, y, and z in this new coordinate system. So let's take a look at how we're going to do that. First, we need definitions. The definitions are very important before we start setting up the triple integral. So let's suppose we have a point in space. Let's put a point in space, maybe right here for drawing purpose. So this is P in space, and we want to give someone location of P by using spherical coordinates. So instead of giving them X direction, Y direction, and Z direction, we're going to give them different ways to find this location of point P. We're going to be using three different things. So we will have rho. This is called rho. We have phi, and we have theta. So the new, I guess the new notation you will see here are these two right here, but theta is the same theta from cylindrical coordinates or polar coordinates. Let's define them. So if that is the point P in space, and I want to give you a location for the point P by these coordinates, so we need the following. Rho, it's going to be the distance from the origin to the point P in space. So this distance is what we call rho. And phi is going to be the angle that opens from the positive z-axis to where that rho is. So this angle is going to be phi. Now theta will give us the sweep on the xy plane. So theta will start from the positive x-axis, and then it will sweep over until you get to that projection of that point P onto the xy plane. So if I drop this down onto the xy plane, let's suppose it's right here. So this is the projection, which will have the coordinate xy and 0. Z coordinate will be 0. So if you find the distance from the origin to this point where we project it down, that's our r in cylindrical, but we're not using r in this. So let's just write it down, but we're not going to use it. We need rho, phi, and theta. We'll redefine them. So theta will be this angle right here. So that is our theta for spherical coordinates. Now, once we understand how to give a location of this point, so this point will be given rho, phi, and theta. Now, we want to define how do we figure out what are our x, y, and z on spherical coordinates. We need to redefine them. What is the expression for x? What is the expression for y? Z in spherical coordinates, and also more importantly, r. What is r in spherical coordinates? So let's go ahead and try to figure something out. So I want you to focus on this area right here. So if you draw this line up here in space, so I know r is right here, you can draw the same angle or the same radius right over here because they're parallel to each other. So that's where I'm going to try to draw. I'll put that same distance right up here in space. And this is r because it's parallel to the same r on the xy plane. So if this is r, then r and z will form this angle, 90-degree angle in space. So if you pull out that triangle, so it looks a little weird, but so stay with me here and try to pay attention. So if you pull this triangle out and try to draw it, so you can understand the relationship between x, y, z, and r, you know angle phi is going to be somewhere right here. So that's our angle phi. That means across from phi should be r. So this is r. That means the hypotenuse is rho, and this distance will be z. So that's this right here. This is going to be z, which is the same distance from here to here. This is z. So I hope you can see that. So now let's work with this triangle and figure out what will be an expression for x, y, and z, also r in spherical coordinates. So by looking at this picture, we know that by our trigonometric functions, sine phi is going to be opposite over hypotenuse. So this is opposite, this is hypotenuse. So sine phi is going to be r over rho. And then if you multiply both sides by rho, you're going to get r is equal to rho sine phi. So this is the very important definition that we need to remember. In spherical coordinates, r is rho sine phi. Now, if you remember that cosine phi is going to be the following. So if you write z in this equation, you're going to get a definition for z. So if I write cosine phi using that same triangle, that's going to be adjacent over hypotenuse. So that would be z over rho, which means now I can write z is going to be rho cosine phi. So there is our next definition. So that means z is going to be rho cosine phi. So we need to figure out what x and y are. So I know r we just discovered that's rho sine phi. So that means we know in polar or cylindrical coordinates, x is r cosine theta, y is r sine theta. That means if we now replace r with our new definition, rho sine phi, into our equations x and y, we're going to get x to be rho sine phi cosine theta. And similarly, y would be rho sine phi sine theta. So these are our new definitions in spherical coordinates for x, y, z, and r. Now we also need to remember that our volume differential, it's going to be dv, which is given as rho squared sine phi d rho d phi d theta. So that's the next thing you're going to have to remember. I'm going to avoid the illustration in this video, but feel free to look up to other resources or in the book how we derive the volume differential if you're using spherical coordinates. So now let's see if we can set up this integral, triple integrals for this particular solid. So E is going to be the solid above this cone within the sphere of radius 1, whose density is given by this formula, and we want to compute the volume of this solid E and Iz. That will be the second moment of mass about the z-axis. Let's go ahead and set it up. So let's imagine what we're given here. So here's our x, y, and z plane. Well, let's see if we can visualize something. So we have a sphere of radius 1. So let's suppose we have a sphere, something like this. So hopefully you can visualize that. Now, all of this is not important. We are probably not going to need a lot of it. Now let's draw the cone. So here's our cone. So the portion we're going to be looking at is this right here. So we have the we have above the cone within the sphere. So this is what we're looking at. This is the solid E. So now here's what we're gonna do. I'm just probably gonna show you how to set up the triple integral, and you can finish up the integration on your own. It's not very difficult. So our solid E, we're going to describe it by using spherical coordinates. So we will need rho to go from where to where. We need phi to go from where to where, and also theta. Now, theta will be the projection of our solid onto the xy plane. So on the xy plane, here's how the projection is going to look like. So you'll create this circle of, so that's what it's going to look like in the xy plane. So if you now set up the bound on rho, well, rho is the distance, as we said. It's going to be the distance from the origin to the solid, so right here. So that's going to be rho, and we know the equation of the sphere is 1, so rho will be from 0 to 1. Phi is the angle from the z-axis to the cone, so phi will be this angle right here. That's phi. So to solve for it, you can actually figure out how to do that. So if you take the equation z is going to be rho cosine phi, and we know x squared plus y squared, square root of that's going to be square root of r squared, and that is just simply r, since we're assuming r is positive, and we know in spherical r is rho sine phi. So then the rho will cancel out. You will have cosine phi is equal to sine phi. And the only way this equation is true or equal to each other when a rho is actually pi over 4. So we know that from trigonometry. So rho is going to go from 0 to pi over 4. There are other places where cosine phi is equal to sine phi, but we're only looking at this angle right here. So we know it's going to be less than pi over 2 because pi over 2 will be all the way here and bigger than 0. So positive angle in the first quadrant, I guess you can think of it that way. So phi will go from 0 to pi over 4. And theta is the angle that sweeps over the entire xy plane to create that solid in the space. So it's going to be this angle right here. So it's going to be entire 0 to 2 pi. So those are the bounds on rho, phi, and theta. Now let's go ahead and set this up. So we're going to set up a triple integral. So the volume of the solid E is going to be the triple integral over the solid E, we're using E in this case, of 1 dV. So we will write this as a spherical coordinate. So we'll have triple integral. Our integrand will be 1 times dV. dV, we know it's rho squared sine phi d rho. So the first integral will go for bound on rho. And we said that that's going to go from 0 to 1. And then the phi is going to go from 0 to pi over 4. And then the theta is going from 0 to 2 pi. So integrating this, it's actually very straightforward, but setting up will be a little bit of work. So that's what I wanted to show you. So please proceed with the integration on your own and figure out what the volume would be. So this is only a setup. Now let's talk about the inertia, about the z-axis for this particular object. So first we need a setup. So the inertia about the z-axis, so the moment of inertia. So that's the second moment of mass. We know this is given for a solid as a triple integral over the solid E of x squared plus y squared times the density function dV. So that is in general. Now we're going to also set this up with spherical coordinates since our solid is best described by using spherical in this case. So we're going to have our triple integral. So the limit of integration will not change. It will be exact same as these right here. So we're just going to recopy them right here. So rho is going to go from 0 to 1. Phi is going from 0 to pi over 4. Theta is from 0 to 2 pi. Exact same limit of integration. And then we have x squared plus y squared. Well, we know x squared plus y squared. In spherical coordinates, this has got to be changed. So I know this is equal to r squared from cylindrical. Now, in spherical, r is rho sine phi. So this is going to be rho sine phi, and we square it, which is really rho squared sine squared phi. So our integrand will have rho squared sine squared of phi. And then density, our density is given in the problem. So it is given right here. It's square root of x squared plus y squared plus z squared. Again, be mindful that in spherical coordinates, x squared plus y squared plus z squared is rho squared. And then you take square root of that. So that's just simply going to be rho, assuming it's positive. So our density will simply be rho. So times rho, and then dV, and we know dV is going to be rho squared times sine phi. Then we have our d rho, d phi, d theta. So this piece right here, this is our volume differential. This piece right here, that's our density simplified in spherical coordinates. And this is right here is our expression for x squared plus y squared in spherical coordinates. Okay, now that's the setup. Now integrating this is also very easy. So I'm gonna leave that up to you. I hope you enjoyed. I'll see you next time. Take care.